Hey everyone, welcome to Calculus 1. This will be lecture 1 of the course. And in this section, we're going to do a little bit like an overview of calculus, a preview of some of the things that are to come in calculus. We just want to hit on a couple of the main motivating use cases that and value adds that calculus brings to mathematics in general. But before we do that, I want to talk quickly about which textbooks I'll be using and which textbooks I recommend you use if you want to follow along with the course closely. So the first book that I will be using is simply called Calculus and Early Transcendentals, and it's a famous book by Larson, Hostetler, and Edwards. Textbook from about 20 years ago, 15, 20 years ago. Should be able to get pretty cheaply on eBay. A good book, has good pedagogy all around, good examples, great flow, very natural, nothing's really missing. It's good stuff. The second book that I'll be using is slightly older, and this is a book called Calculus and Analytic Geometry. I would say this is probably from the 90s by Thomas and Finney. And again, very good examples. I'll be pulling a lot of examples from this book. And then the last book is called The Calculus with Analytic Geometry. And this is kind of a classic calculus textbook by Louis Leithold. I really think of this as sort of the granddaddy of calculus textbooks. Came out around maybe the 60s, 70s, a little bit older. But really, if you want to go back and review like how calculus used to be taught back in the day, this is a good one for that. So in order of priority, I would say Calculus and Early Transcendentals is the one that I'll be using the most, followed by this guy, and then finally Louis Leithold. Okay, so let's go ahead and jump into the section. So again, as I was saying, we want to do a little bit of a preview of calculus here, and that's what this section is going to be about. We'll call it section 1.1, calculus preview. Now, calculus is a name you've certainly heard. Even if you're not a mathematician, you probably heard of calculus. Even if you have no mathematics background, you might have heard of calculus. And that's because it is a vast area in mathematics and extremely important to all of the sciences. There are really countless applications of calculus, and its importance really can't be overstated. What I want to do in this section is just look at a couple of the key capabilities that calculus enables. We obviously won't go into the the endless examples of applications that these capabilities enable. But we'll touch on a couple, okay? And so this list is by no means exhaustive. Just keep that in mind. This is by no means exhaustive, okay? And so on the one side, we've got without calculus, and the other side, we've got with calculus. And so in the algebra world, we're very familiar with the idea of identifying the value of a function when x is equal to a specific value, like x equals c. That's just called evaluating the function. We've done that many, many times in algebra. Now in calculus, this idea gets extended a little bit further. And so what we do in calculus is, what calculus enables is, it enables us to identify the value of a function as x gets close to a specific value. And when we say close, what we really mean is infinitely close. That's really that captures the idea a little bit better, right? And another way this is frequently expressed is by saying arbitrarily close, right? But what we really mean is very, 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 very close, like as close as you want, i.e. infinitely close. Although this is a little bit of an abuse of terminology, but it gets the idea across a little bit better than if I say arbitrarily close. And so this is the idea that is captured by the limit concept. And so that'll be the maiden topic of Calc 1. We'll talk about limits. And it really forms the backbone of a lot of the other capabilities that calculus enables. That's hence the reason we study it first. Okay, so that's the first big example. Okay, the second big example has to do with slope. Okay, and so in the algebra world, we're used to being able to identify the slope at a specific point on a straight line. Now, the key here being straight line. Okay, now if I want to know the slope at this particular point right here, and it happens to be on a straight line, well, the slope at that point is the same as the slope at any point on this line, right? It's just going to be the slope of the line. And so we know m is equal to the rise over the run, and that's how we identify the slope of a straight line, and hence the slope at any point on a straight line. Now in calculus, what we're going to do is we're going to blow that idea up, right? Instead of being able to identify the slope at a specific point on a straight line, we're going to be able to identify the slope at a specific point on a curve. And that's huge. So if I have an arbitrary function like this in the plane, just looks like a parabola in the plane, and I want to know the slope of this point on this curve, then I can't do that without calculus. And in the algebra world, how am I going to do that? I can't do it. In the calculus world, I use what is called the derivative, which we have notation for here, right? So once we learn limits, then we'll jump into derivatives. Derivatives are built using machinery of limits, so these ideas kind of all build on each other. And so we start with limits, and we move to derivatives. Okay, so that's the second really big idea. And it doesn't have to be a curve like this. It can be a curve as crazy as you like, which is amazing. All right. The third really big idea, really big application in calculus has to do with areas. So in the world of algebra, we're used to being able to identify the area of rectilinear shapes. So you give me a rectangle, you know the base and the height, I can tell you the area is just base times height. If you give me a triangle, I can also tell you the area. You give me a circle, I can tell you the area of that. And there's a lot of shapes that we can identify the area of just using algebra, right? But as soon as the shape becomes kind of different, not well understood, not a typical sort of shape, then we run into problems. In calculus, we can deal with these types of questions, the area of rando shapes, very efficiently. And so in calculus, we gain the ability of identifying the area under an arbitrary curve. All right, that's Calc 1. Calc 2, it even gets better, and Calc 3, it's even better than that. So let's say we have a function in the plane that looks like this when we plot it. Now, if I want to know the area underneath that function between the verticals here and the x-axis, if I want to identify this area here, how am I going to do that with algebra? Well, it's going to be real difficult. Probably not going to be able to do it with algebra. But with calculus, it's a simple matter. This is what's called the integral. And so the integral is the third very large application of calculus, right? And it's actually the subject matter of calculus 2 we pick up right away with integration, right? So in calculus 1, we learn limits, and then we learn differentiation, and then in calculus 2, we learn integration and a whole bunch of other stuff. Right, so when it turns out using calculus, we can find the area not just underneath curves, but between curves. If I want to know this area, I can identify it. I can even identify surface area of shapes in space using calculus. I can identify cross-sectional areas of random shapes. The sky's the limit. Huge application, really revolutionary stuff, very interesting. And that'll come in calculus 2. Now, those I would say are the big three. So you've got limits, derivatives, differentiation, and integrals or integration. Those are kind of the big three ideas in calculus. And then, as I said, these ideas spin up about 1,000 applications each, just in Calc 1, 2, and 3, right? And so one such application is this one. And so in the world of algebra, if you give me 2 points in the plane, I can tell you the distance between them, the distance of the straight line that connects them, right? But if this isn't a straight line, if instead it's, got some curvature to it, I can't really do it. I can't really use algebra to figure out what the distance is for like a curved line. In calculus, however, that capability is fundamental, right? So if you give me a random looking curve like this, in calculus, I can find the distance along that curve. Very cool, right? Very cool. This is an application that uses the machinery that we just saw, right? And this is one that we'll talk about in this class. Another big application is finding the center of mass, right? So if you give me a rectangle or a circle or a triangle, I can identify the center of mass pretty easily if it's a well-known shape like that. But what if it's an arbitrary region? Again, in calculus, we gain the ability to identify the center of mass of arbitrary shapes, not just shapes that are well known and simple to understand. So if you give me a function that looks like this, I can identify the center of mass maybe of this kind of a region, right? And I can use calculus to do that. Can't do that with algebra, but we can do it with calculus. Okay, and so this has been just a quick introduction to some of the things that we're going to be talking about in this class. There are, as I said, many more examples of value adds for math that come from calculus. And we're going to explore these throughout the course. We'll learn a concept, we'll develop applications based on that concept, and then we'll move on to new concepts and new applications. And so there's just tons and tons of it. Calculus, really, you can think of calculus as kind of the backbone of modern science, of modern engineering. It really is the most application-filled area of mathematics in all, probably. So anyways, we'll leave it there. That'll do it for this lecture. Thank you very much for watching the video. Please let me know as we start to produce more of these videos if there's any way I can improve them, and stick with it. We will this will be a full calculus course, end to end. We're not going to skip anything. We're going to cover every topic, and we're going to do lots and lots of examples. Use this class to supplement whatever whatever calculus formal education you're working on, or for just review. Anyways, it's great to have you here, and we'll talk to y'all next time. Take care.